Hi everyone, my name is Huan Nguyen, and in this video, I'll explain what I did to improve the performance of my classifier, what I did to access and improve the fit of my model. My objective was to maximize ROC, AUC on the UCI Bank marketing dataset while ensuring that the final model generalizes well, is well fitted and not overfitting or underfitting. I approached this systematically through pre-processing optimization, imbalance experimentation, model comparison, learning curve diagnostics, feature engineering testing, AutoML refinement, and finally ensembling for leaderboard improvement. In terms of improving model performance for the pre-processing pipeline, my final pre-processing pipeline consists of winsorizing, clipping outliers, standardization of numerical features, one-hot encoding of categorical variables. Winsorization was used because the dataset contains extreme values in features such as balance and campaign. Instead of removing these observations, I clipped extreme value to reduce variance while preserving information. Scaling ensured stability for logistic regression, as well as more consistent gradient optimization for boosting algorithms. Although tree-based models do not strictly require scaling, I kept the pre-processing consistent across experiments. In terms of handling class imbalance, I experimented with SMOTE. Because the data set is imbalanced, I initially applied SMOTE after pre-processing to oversample the minority class. I then trained five baseline models such as logistic regression, decision tree, random forest, XGBoost, and gradient boosting machine. Each model included the learning curves based on its ROC, AUC of its training and cross-validation dataset. In terms of the baseline model comparison, the first model was a logistic regression, and it seemed to be fairly well fitted. However, its cross-validated ROC AUC is still relatively low, signaling that we can do a little bit better. Then I moved on to a decision tree, and the decision tree exhibits extreme patterns of overfitting. As we can see, the gap from the training and cross-validation AUC is very large and does not converge regardless of the increase in the training samples. Moving on to the random forest was a little bit better than the decision tree, but also was still also overfitting as the gap from train and cross-validation of AUC was still very, very high and did not converge even though training samples increased. Moving on to our GBM model seems to be well fitted as the training and cross-validation ROC AUC is relatively narrow and converges as the training samples increases. And we can almost see the same thing with our XG boosting model, which indicates that XG boosting model and the GBM model are well fitted for our data set and for our business objective. Both XGB Boost and GBM showed high validation AUC, much better than our logistic regression, converging learning curves, also small train validation gap. At this stage, boosting models were clearly dominant. But I am also aware that these boosting models can handle class imbalance without the addition of smoke. Interestingly, when I removed smoke and trained GPM directly on the original imbalance dataset, performance improved slightly. And this makes conceptual sense as boosting methods naturally focus on hard to classify examples. Tree-based models handle imbalance through splitting criteria, and Smoke can introduce a lot of synthetic noise and distort feature space. After removing Smoke, validation ROC and AUC increased. Learning curves remained stable, and the train and validation gaps stayed relatively small. This was a key decision. It shows that pre-processing must be model specific rather than universally applied. Next, I wanted to experiment with feature engineering experiments. I engineered several domain-inspired features such as ever contacted, recently contacted, campaign high, H-band, balance positive, contact secular. These were designed to capture whether they have prior engagement history, campaign intensity, age segmentation, and simplified financial indicators. However, after retraining our best GBM model, validation ROC and AUC dropped slightly, learning curve did not improve drastically, and the model complexity increased. This indicates that boosting models were clearly capturing nonlinear interactions internally. Therefore, the additions of these featured engineers introduced noise and model complexities that reduced its performance. I then removed these engineered features. After I've been able to finalize and understand that the best pre-processing workflow is winterizing, scaling one hot code encoding without using Smote and without the engineered features, I then moved on to the AutoML refinement. Um, After having the optimal pre-processing strategy, I ran H2O AutoML restricted to specifically XG boosting and gradient boosting. I limited AutoML to boosting families because earlier experiments showed they clearly outperformed linear bagging methods and logistics regression. AutoML performed hyperparameter optimization, regularization tuning, model variant exploitations, and class imbalance handling specific to each model. I selected the highly optimized GBM configurations as the best individual model based on which model performs the best in terms of cross-validation, ROC, and AUC. To further even improve Kaggle performance, I ensembled the top performing AutoML boosting models. Instead of relying on a single best GBM, I combined predictions from the best GBM model, the best XGBoost model, used averaging for predicted probabilities, and ensembling was able to improve my performance because different boosting configurations capture slightly different decision boundaries, and averaging those decisions reduces variance and smooths prediction noise. After ensembling, Kaggle, ROC, and AUC improved, cross-validation performance remained stable, and there was no significant increase in overfitting was observed. For each model, to assess the model fit, I plotted the learning curves using ROC and AUC. For the final model of GBM and XGBoost models, training AUC gradually decreased as sample size increased. Validation AUC increased and stabilized. The gap between curves remained very small. This indicates that controlled variance, sufficient model complexity, and good generalization. Earlier models, such as logistic regressions, uh, exhibits patterns of underfitting. A single decision tree or random forest had very high variance, which is susceptible for overfitting. The boosted models achieve lower bias than linear models, lower variance than a single tree or a random forest, and converging learning curves. After tuning and removing smoke, bias and variance were balanced. There wasn't any widening training or validation gap that occurred, and validation performance remained strong. The final ensemble boosting model showed high validation, ROC and AUC, stable cross and validation scores, small training validation gap, and significant improve on Kaggle performance. There is very little evidence of overfitting because validation and leaderboard results align. There is also very little evidence of underfitting because performance is high and curves do not plateau at low values. Therefore, the final ensemble is well fitted. The project reinforced and utilized several important insights. Smote is not universally beneficial. Tree-based boosting often handles class imbalance naturally and efficiently. Feature engineering must be validated empirically. Learning curves are essential diagnostic tools, and ensembling can improve performance without increasing overfitting if models are stable. To summarize, I optimized pre-processing through winterizing and encoding. I tested and removed smoke for boosting models. I empirically validated feature engineering. I refined boosting models using AutoML and improved its performance on Kaggle using ensembling. And I confirmed the model fit through learning curves and bias variance analysis. The final result is a high-performing, well-fitted ensemble boosting model that generalizes effectively. Thank you very much.